Imagine you have an image, but it's represented by numbers. Your task is to flip this image horizontally, like looking in a mirror, and then change all its colors. Today's problem is flipping an image. Take a moment. What would you do to solve this? Alright, let's dive into the problem statement. We're given a square image, which is represented as a two-dimensional grid of numbers. Think of it like a spreadsheet, where each cell contains either a 0 or a 1. These zeros and ones represent pixels. A 1 might be a white pixel, and a 0 might be a black pixel. So, our input is essentially a grid of binary numbers, meaning only zeros and ones. The problem asks us to perform two operations on this image. First, we need to flip the image horizontally. This means that for each row in our grid, the elements on the left side should move to the right side, and the elements on the right side should move to the left. It's exactly like reversing a list of numbers. For example, if a row is 1, 0, 0, after flipping it horizontally, it becomes 0, 0, 1. The element that was first is now last, the second is now second to last, and so on. The second operation is to invert the image. After flipping each row, we then need to change every 0 to a 1 and every 1 to a 0. This is a simple transformation. If you see a 0, replace it with a 1. If you see a 1, replace it with a 0. So if our flipped row was 0, 0, 1, after inverting it becomes 1, 1, 0. 0 becomes 1, 0 becomes 1, and 1 becomes 0. Let's look at a full example. If our input image has a row like 1, 1, 0, first we flip it horizontally. The 1 at the beginning moves to the end, the 0 at the end moves to the beginning. So 1, 1, 0 becomes 0, 1, 1. Now we invert this new row. 0 becomes 1, 1 becomes 0, and the final 1 becomes 0. So 0, 1, 1 transforms into 1, 0, 0. This is what we need to do for every single row in the entire image. The constraints tell us that the image will always be square, meaning it has the same number of rows as columns, and its size will be between 1 and 20. This means our grids won't be huge, which is helpful to keep in mind. The values inside the grid will only ever be 0 or 1. The challenge here is performing these two distinct operations efficiently, especially when they interact with each other. The most obvious thing to try, when faced with two distinct operations like flipping and inverting, is to simply perform them one after the other, exactly as described. For each row in our image, we can first completely reverse that row. Imagine we have a row of numbers. We can take the first element and swap it with the last, then take the second element and swap it with the second to last, and continue this process until the entire row is reversed. Once a row is fully reversed, we then iterate through that same row again, element by element. For each element, if it's a 0, we change it to a 1. If it's a 1, we change it to a 0. We repeat this two-step process for every single row in the image. So for an image with n rows and n columns, we would first loop through each of the n rows. Inside that loop, to reverse a row, we might perform about n swap operations. After reversing, we would then loop through that same row again, performing n inversion operations. This means for each row, we're doing roughly n operations for reversing, and then another n operations for inverting. Since we do this for n rows, the total number of operations would be roughly n multiplied by n plus n, which simplifies to n multiplied by 2n, or 2n squared. This gives us a time complexity of O of n squared. This means that if our image size doubles, the time it takes to process it roughly quadruples. For space complexity, since we are modifying the image directly in place and not creating any new large data structures to store intermediate results, our space complexity is O of 1, meaning it uses a constant amount of extra memory regardless of the input size. While this approach works, it feels like we're doing two separate passes over the data for each row. Can we be more clever and combine these operations? The key insight to optimize this problem is to combine the flipping and inverting operations into a single pass for each row. Instead of reversing a row completely and then going back to invert it, we can do both at the same time as we're swapping elements. This is where the two pointers pattern comes in handy. Imagine you have a row of numbers. We'll use 2 pointers. Let's call them left and right. The left pointer starts at the very beginning of the row, pointing to the first element. The right pointer starts at the very end of the row, pointing to the last element. Our goal is to move these pointers towards each other, processing elements as they meet. We'll continue this process as long as the left pointer is less than the right pointer. Inside this loop, we want to swap the elements that left and right are pointing to, but we also want to invert them simultaneously. So we'll take the value at the left pointer, invert it, and place it where the right pointer was. Then we'll take the value at the right pointer, invert it, and place it where the left pointer was. To do this correctly, we need a temporary storage spot. We'll store the original value at the left pointer in a temporary variable. Then we can update the element at the left pointer with the inverted value from the right pointer. After that, we update the element at the right pointer with the inverted value that we saved in our temporary variable. After each swap and invert, we move the left pointer 1 step to the right and the right pointer 1 step to the left, bringing them closer together. What happens if the row has an odd number of elements? Eventually, the left and right pointers will meet in the middle, pointing to the same element. Our loop condition, left less than right, will stop the main swapping process, but that middle element still needs to be inverted. So after the loop finishes, we add a check. If left is now equal to right, it means there's a single middle element that hasn't been touched yet. In this case, we simply invert that one middle element. This approach processes each pair of elements, or a single middle element, only once, combining the two operations into one efficient pass. We still iterate through n rows, and for each row, we perform roughly n divided by 2 operations. This still results in an O of n squared time complexity, but it's more efficient in practice because we're doing less work per element. The space complexity remains O of 1 because we're still modifying the image in place and only using a few extra variables for our pointers and temporary storage. Let's trace our optimized algorithm with an example. Our input image is a grid. The first row is 1, 1, 0, the second row is 1, 0, 1, and the third row is 0, 0, 0. The size n is 3 since it's a 3 by 3 grid. We start by looping through each row. For the first row, which is 1, 1, 0, we initialize our left pointer to 0 and our right pointer to n-1, which is 2. So left is 0, right is 2. The condition left less than right is true because 0 is less than 2. We enter the loop. We store the value at image at row 0, column left, which is 0, into a temporary variable, so temp becomes 1. Now we update image at row 0, column left. We set it to 1 minus the value at image at row 0, column right. The value at image at row 0, column right is 0, so 1 minus 0 is 1. Image at row 0, column 0 becomes 1. Next, we update image at row 0, column right. We set it to 1 minus our temp variable. Temp was 1, so 1 minus 1 is 0. Image at row 0, column 2 becomes 0. At this point, our row is 1, 1, 0. We increment left to 1 and decrement right to 1. Now left is 1, right is 1. The condition left less than right is false because 1 is not less than 1. The loop ends. We check if left equals right. Yes, 1 equals 1. So we need to invert the middle element. Image at row 0, column left, which is 1, is currently 1. We set it to 1 minus 1, which is 0. So image at row 0, column 1 becomes 0. The first row is now 1, 0, 0. We move to the second row, 1, 0, 1. Left is 0, right is 2. Left is less than right. We store image at row 1, column 0, which is 1, into temp. Temp is 1. Image at row 1, column 0 becomes 1 minus image at row 1, column 2, which is 1. So 1 minus 1 is 0. Image at row 1, column 0 becomes 0. Image at row 1, column 2 becomes 1 minus temp, which was 1. So 1 minus 1 is 0. Image at row 1, column 2 becomes 0. The row is now 0, 0, 0. We increment left to 1, decrement right to 1. Left is 1, right is 1. Left is not less than right. Loop ends. Left equals right. We invert the middle element. Image at row 1, column 1 is currently 0. We set it to 1 minus 0, which is 1. Image at row 1, column 1 becomes 1. The second row is now 0, 1, 0. Finally, the third row 0, 0, 0. Left is 0, right is 2. Left is less than right. We store image at row 2, column 0, which is 0 into temp. Temp is 0. Image at row 2, column 0 becomes 1 minus image at row 2, column 2, which is 0. So 1 minus 0 is 1. Image at row 2, column 0 becomes 1. Image at row 2, column 2 becomes 1 minus temp, which was 0. So 1 minus 0 is 1. Image at row 2, column 2 becomes 1. The row is now 1, 0, 1. We increment left to 1, decrement right to 1. Left is 1, right is 1. Left is not less than right. Loop ends. Left equals right. We invert the middle element. Image at row 2, column 1 is currently 0. We set it to 1 minus 0, which is 1. Image at row 2, column 1 becomes 1. The third row is now 1, 1, 1. And there's our final result. The image is transformed into a new grid. The first row is 1, 0, 0. The second row is 0, 1, 0. And the third row is 1, 1, 1. This output is correct because each row has been flipped horizontally and then all its values inverted. You'll spot the two pointers pattern when you need to process elements from both ends of a list or array simultaneously, often moving towards the center. This is especially useful for problems involving reversing, finding pairs, or checking for palindromes. Another signal is when you have two operations that can be combined, like reversing and transforming, on the same set of data. The time complexity for our optimized solution is O of n squared, because we iterate through n rows, and for each row, we perform roughly n operations. The space complexity is O of 1, as we only use a few constant extra variables. This two pointers technique is incredibly versatile. Try the next problem that involves reversing or pairing elements. You might find the same pattern applies. Don't forget to like and subscribe for more DSA insights.